Green's theorem is a fundamental result in vector calculus that relates a line integral around a simple closed curve, C, to a double integral over the plane region, D, bounded by C. It is essentially a two-dimensional version of the more general Stokes theorem. Mathematical statement. Green's theorem states that for a continuously differentiable vector field, \math f equals p, q, defined on an open region containing D and its boundary, C. Contour integral C p dx plus q dy equals indefinite integral d x q y p. The here \oint_c denotes the line integral around the closed curve C. \tint_d denotes the double integral over the region D. P and Q are the components of the vector field \math f. \frac \partial q \partial x and \frac \partial p \partial y are partial derivatives of q and p with respect to x and y, respectively. Intuitive explanation. Green's theorem can be understood as a way to convert a circulation or flux around a boundary into a sum of local rotations or divergences within the region. Line integral, the left side of the equation, \oint_c p, dx and q, dy, represents the circulation of the vector field, \math f, around the closed curve, C. This measures how much the vector field flows along the boundary. Double integral, right side, \tint_d \left, \frac \partial q \partial x \frac \partial p \partial y \right. The represents the total curl of the vector field within the region D. The expression \frac \partial q \partial x \frac \partial p \partial y is the curl or rotation of the vector field in 2 dimensions. Applications. Green's theorem has several important applications in physics and engineering, including fluid dynamics. It helps in analyzing the circulation and flux of fluid flow around obstacles. Electromagnetism. It is used to relate the circulation of electric and magnetic fields to their sources. Area calculation. Green's theorem can be used to compute the area of a region D by choosing appropriate P and Q. Example. Consider a vector field \math f equals y, x, and a region D bounded by the unit circle x2 plus y2 equals 1. Line integral. Parameterize the unit circle as \math r t equals \cos t \sin t 4 t \in 0 2 pi. Compute \oint_c y dx x dy. Double integral. Compute \tint_d \left \frac \partial x \partial x \frac \partial y \partial y \right. The simplify to \tint_d -1 1 the equals -2 \tint_d the area of D is \pi, so the double integral is -2 \pi. Both methods should yield the same result, illustrating Green's theorem in action. Conservative vector fields. A vector field \math f equals p, q is called conservative if there exists a scalar potential function \phi such that f equals x, y. In other words, the vector field \math f is the gradient of some scalar function \phi. Properties of conservative vector fields. Path independence. The line integral of a conservative vector field between 2 points is independent of the path taken. Zero curl. A conservative vector field has zero curl. Mathematically, this means xqyp equals 0 connection to Green's theorem. Green's theorem states contour integral C p dx plus q dy equals indefinite integral d xqyp. For a conservative vector field, we have \frac \partial q \partial x \frac \partial p \partial y equals 0. Substituting this into Green's theorem gives contour integral C p dx plus q dy equals indefinite integral d0 that equals 0. This result tells us that the line integral of a conservative vector field around any closed curve, C, is 0. This is a direct consequence of the fact that the circulation of a conservative vector field around a closed loop is 0, reflecting the path independence property. Implications. Identifying conservative fields. Green's theorem can be used to test whether a given vector field is conservative. If the line integral around every closed curve is 0, the vector field is conservative. Finding potential functions. If a vector field is conservative, we can find a potential function \phi such that \math f equals \nabla \phi. This involves solving the partial differential equations x equals pan y equals q. Example: consider the vector field \math f equals y x. Check for conservativeness. Compute the curl \frac \partial x \partial x \frac \partial y equals 1 to 1 equals 0. Since the curl is 0, \math f is conservative. Find potential function. Solve \frac \partial phi partial x equals y and \frac partial phi partial y equals x. Integrate \frac partial phi partial x equals y with respect to x \phi equals xy plus gy. Differentiate \phi with respect to y \frac partial phi partial y equals x plus gy equals x. This implies gy equals 0, so gy is a constant. Therefore, \phi equals xy. A potential function \phi is a scalar function whose gradient is equal to a given vector field \math f. In mathematical terms, if \math f equals p q is a vector field, then \phi is a potential function if f equals sad smiley x y. This means that the vector field \math f can be expressed as the gradient of \phi. Conditions for existence. For a vector field \math f equals p q to have a potential function \phi, it must be conservative. This implies two main conditions: path independence. The line integral of \math f between any 2 points is independent of the path taken. 0 curl. The curl of \math f must be 0 xqyp equals 0. Finding a potential function. To find a potential function \phi for a conservative vector field \math f equals p q, follow these steps. Integrate p with respect to x. Start with \frac partial phi partial x equals p. Integrate p with respect to x to get \phi x y equals indefinite integral p dx plus g y. Here, g y is an arbitrary function of y because the partial derivative with respect to x does not affect y. Differentiate with respect to y. Differentiate \phi with respect to y equals y indefinite integral p dx plus g y equals y indefinite integral p dx plus g y. Set this equal to q equals y indefinite integral p dx plus g y. Solve for g y. Rearrange to solve for g y equals q y indefinite integral p dx. Integrate g y with respect to y to find g y. Combine results. Substitute g y back into the expression for \phi to get the potential function. Example: consider the vector field \math f equals 2xy x caret 2 plus 2y. Integrate p equals 2xy with respect to x. Phi xy equals indefinite integral 2xy dx equals x2y plus hy. Here, hy is an arbitrary function of y. Differentiate with respect to y. Y equals x2 plus hy. Set this equal to q equals x caret 2 plus 2y x2 plus hy equals x2 plus 2y. Solve for hy. Hy equals 2y. Integrate hy with respect to hy equals y2 plus c. Combine results. Phi xy equals x2y plus y2 plus c. So, the potential function \phi for the vector field \math f equals 2xy x caret 2 plus 2y is \phi x y equals x caret 2y plus y caret 2 plus c. The concept of potential functions is closely related to the work done by a force field. Let's explore this relationship in detail. Work done by a force field. In physics, the work W done by a force field \math f when moving an object along a path c from point A to point B is given by the line integral of the force field along the path. W equals indefinite integral cf dr. Here, \math f is the force field. D\math r is the differential displacement vector along the path c. \math f \d\math r represents the dot product of the force field and the displacement vector. Potential functions and conservative force fields. A force field, \math f, is conservative if it can be expressed as the gradient of a scalar potential function, \phi, f equals. The negative sign indicates that the force field points in the direction of decreasing potential. Relationship to work. For a conservative force field, the work done by the force field when moving an object from point A to point B depends only on the values of the potential function at these points, not on the path taken. This is a direct consequence of the path independence property of conservative fields. The work done by a conservative force field is given by W equals indefinite integral CF dr equals phi of phi b. This means that the work done is equal to the difference in the potential function values at the starting and ending points. Intuitive explanation. Path independence. For conservative force fields, the work done is independent of the path taken between 2 points. This simplifies calculations, as we only need to know the potential function values at the endpoints. Energy interpretation. The potential function, \phi, can be interpreted as the potential energy associated with the force field. The work done by the force field corresponds to the change in potential energy. Example: consider the gravitational force field near the Earth's surface, which is conservative. The potential function, \phi, for the gravitational force, \math f, equals mg_j, where g is the acceleration due to gravity and \j is the unit vector in the vertical direction, is phi y equals mgy. If an object moves from height y_1 to height y_2, the work done by the gravitational force is W equals phi y1 phi y2 equals mg y1 y2. This shows that the work done by gravity depends only on the initial and final heights, not on the path taken. Gravitational potential energy, U, is the energy an object possesses due to its position in a gravitational field. For an object of mass, m, at a height, y, above a reference point, usually the Earth's surface, the gravitational potential energy is given by U equals mgy. Here, g is the acceleration due to gravity, y is the height above the reference point. Connection to potential functions. In the context of gravitational fields, the potential function, \phi, represents the gravitational potential energy per unit mass. For a gravitational force field, \math f equals mg_j, the potential function, \phi, is phi y equals gy. The gravitational force field can be expressed as the negative gradient of this potential function, f equals dy dj caret equals gj caret. Work done by gravitational force. The work, W, done by the gravitational force when moving an object from height y_1 to height y_2 is given by the change in gravitational potential energy. W equals U y1 U y2 equals mg y1 y2. This is consistent with the general relationship for conservative force fields, where the work done is equal to the difference in the potential function values at the endpoints. Intuitive explanation. Potential energy. The gravitational potential energy, U equals mgy, represents the energy stored in an object due to its position in the gravitational field. Higher positions correspond to higher potential energy. Work and energy. When an object moves in a gravitational field, the work done by the gravitational force results in a change in the object's potential energy. If the object moves downward, the gravitational force does positive work, and the potential energy decreases. If the object moves upward, the gravitational force does negative work, and the potential energy increases. Example: consider an object of mass, m, moving from a height y_1 equals 10 meters to a height y_2 equals 5 meters. Initial potential energy, U y1 equals mg10. Final potential energy, U y2 equals mg5. Work done. W equals U y1 U y2 equals mg 10 5 equals 5 mg. This shows that the work done by the gravitational force is equal to the decrease in gravitational potential energy. Conclusion: gravitational potential energy is a specific example of the broader concept of potential functions in conservative force fields. It quantifies the energy associated with an object's position in a gravitational field and provides a straightforward way to calculate the work done by gravitational forces. This relationship is fundamental in mechanics and helps us understand energy conservation and the behavior of objects under gravity. What is kinetic energy? Kinetic energy is the energy that an object possesses due to its motion. It depends on both the mass of the object and its velocity. The faster an object moves and the more massive it is, the greater its kinetic energy. Mathematical formula. The kinetic energy, Ke, of an object can be calculated using the following formula. Ke equals 21 mv2. Here m is the mass of the object, v is the velocity of the object, \frac 1, 2 is a constant factor. Units of kinetic energy. In the International System of Units (SI), kinetic energy is measured in joules, J. 1 joule is equivalent to 1 kilogram meter squared per second squared, \text, kilogram, \text, m2 / text, s2. Intuitive explanation dependence on mass. If two objects are moving at the same velocity, the one with the greater mass will have more kinetic energy. For example, a truck moving at 60 km per hour has more kinetic energy than a bicycle moving at the same speed. Dependence on velocity, kinetic energy increases with the square of the velocity. This means that if you double the velocity of an object, its kinetic energy increases by a factor of 4. For instance, a car moving at 100 km per hour has 4 times the kinetic energy of the same car moving at 50 km per hour. Examples of kinetic energy moving vehicles, cars, bicycles, and airplanes all have kinetic energy due to their motion. The faster they move, the more kinetic energy they possess. Falling objects. An object falling under the influence of gravity gains kinetic energy as it accelerates towards the ground. Sports. A soccer ball kicked across a field, a tennis ball hit by a racket, and a baseball thrown by a pitcher all have kinetic energy. Relationship to potential energy. Kinetic energy is often discussed in conjunction with potential energy. Potential energy is the energy stored in an object due to its position or configuration. For example, an object held at a height has gravitational potential energy. When it falls, this potential energy is converted into kinetic energy. Conservation of energy. In a closed system, the total energy, kinetic and potential, remains constant. This is known as the conservation of energy principle. For example, when a pendulum swings, its energy continuously converts between kinetic and potential forms, but the total energy remains constant. Example calculation. Let's calculate the kinetic energy of a 2 kg object moving at a velocity of 3m/s. Given mass m equals 2 kg, velocity v equals 3m/s. Formula K equals 21 mv2. Calculation K equals 21 2 kg 3m/s 2 equals 21 2 9 equals 9 j. So, the kinetic energy of the object is 9 joules. Conclusion. Kinetic energy is a fundamental concept in physics that describes the energy of motion. It plays a crucial role in understanding the dynamics of objects and systems. By analyzing kinetic energy, we can gain insights into the behavior of moving objects and the principles governing their motion. Green's theorem is a fundamental result in vector calculus, and its creation is attributed to the British mathematician George Green. Let's explore the historical context, the development process, and the significance of Green's theorem in detail. Historical context. George Green, 1793 to 1841. George Green was a self-taught mathematician and physicist born in Nottingham, England. Despite having limited formal education, Green made significant contributions to mathematics and physics. His work laid the foundation for several important concepts in these fields. Development of Green's theorem. Green's essay, 1828. The origins of Green's theorem can be traced back to Green's 1828 essay titled An Essay on the Application of Mathematical Analysis to the Theories of Electricity and Magnetism. In this essay, Green introduced several key ideas that would later become central to vector calculus. Potential theory. Green's essay focused on potential theory, which deals with scalar potential functions and their applications in physics, particularly in the study of electric and magnetic fields. Green's identities. Green introduced what are now known as Green's identities, which are integral identities involving scalar and vector fields. These identities are crucial in the study of partial differential equations and potential theory. Green's theorem. One of the most significant results from Green's essay is what we now call Green's theorem. Green's theorem relates a line integral around a simple closed curve to a double integral over the region enclosed by the curve. This theorem provides a powerful tool for converting complex line integrals into more manageable double integrals. Mathematical formulation. Green's theorem states that for a continuously differentiable vector field, \math f equals p, q, defined on an open region containing D and its boundary, C. Contour integral C p dx plus q dy equals indefinite integral d x q y p. The here \oint_c denotes the line integral around the closed curve C. \tint_d denotes the double integral over the region D. P and Q are the components of the vector field \math f. backslash frac, backslash partial q, backslash partial x, and backslash frac, backslash partial p, backslash partial y are partial derivatives of q and p with respect to x and y, respectively. Significance and applications. Green's theorem has profound implications in both mathematics and physics. Some of its key applications include fluid dynamics. Green's theorem helps analyze the circulation and flux of fluid flow around obstacles, making it essential in the study of fluid dynamics. Electromagnetism. In electromagnetism, Green's theorem is used to relate the circulation of electric and magnetic fields to their sources, aiding in the understanding of electromagnetic phenomena. Area calculation. Green's theorem can be used to compute the area of a region by converting a line integral around the boundary into a double integral over the region. Mathematical analysis. Green's theorem is a special case of the more general Stokes theorem, which extends the concept to higher dimensions and more complex surfaces. Legacy of George Green. Despite his significant contributions, George Green's work was not widely recognized during his lifetime. It was only after his death that his essay gained attention, thanks to the efforts of mathematicians like William Thomson, Lord Kelvin, and George Gabriel Stokes. Today, Green's theorem is a cornerstone of vector calculus and is taught in mathematics and physics courses worldwide. Conclusion. Green's theorem, developed by George Green in his 1828 essay, is a pivotal result in vector calculus that bridges the gap between line integrals and double integrals. Its creation marked a significant advancement in mathematical analysis and has had lasting impacts on various scientific fields. Green's work exemplifies the profound contributions that can arise from a deep understanding of mathematical principles. Even in the absence of formal education, the geometric interpretation of Green's theorem provides a visual and intuitive understanding of the relationship between a line integral around a closed curve and a double integral over the region it encloses. Let's break it down step by step. Green's theorem recap. Green's theorem states that for a continuously differentiable vector field, \math f equals p, q defined on an open region containing d and its boundary, c. Contour integral c p dx plus q dy equals indefinite integral d x q y p. The geometric interpretation line integral around the boundary, the left side of Green's theorem, \oint_c p dx and q dy represents the circulation of the vector field, \math f around the closed curve c. Geometrically, this measures how much the vector field flows along the boundary of the region d. Double integral over the region, the right side, \tint_d \left, \frac, \partial q, \partial x, \frac, \partial p, \partial y, \right, the represents the total curl or rotation of the vector field within the region d. The expression \frac, \partial q, \partial x, \frac, \partial p, \partial y is the z component of the curl of \math f in 2 dimensions. Visualizing the theorem, imagine a flat, 2-dimensional region D with a boundary C. The vector field \math f is defined over this region. Here's how to visualize the theorem: circulation, boundary flow picture walking along the boundary C of the region D. As you walk, you measure how much the vector field \math f pushes you along your path. This is the line integral \oint_c p dx and q dy. Curl, internal rotation. Now, imagine looking at the entire region D. At each point inside D, you measure the local rotation or twist of the vector field \math f. This local rotation is given by \frac, \partial q, \partial x, \frac, \partial p, \partial y. The double integral \tint_d \left, \frac, \partial q, \partial x, \frac, \partial p, \partial y, \right. The sums up all these local rotations over the entire region. Intuitive understanding. Green's theorem essentially states that the total circulation of the vector field around the boundary C is equal to the sum of all the local rotations within the region D. This can be thought of as a balance between the boundary behavior and the internal behavior of the vector field. Example: consider a vector field \math f equals y, x, and a region D bounded by the unit circle x2 plus y2 equals 1. Line integral circulation parameterize the unit circle as \math r t equals \cos t, \sin t 4 t \in 0 2 \pi. Compute \oint_c y dx x dy. double integral, curl compute, backslash tint underscore d backslash left, backslash frac, backslash partial x, backslash partial x, backslash frac, backslash partial y, backslash right, the simplify to backslash tint underscore d minus 1, 1, the equals minus 2 backslash tint underscore d the area of d is backslash pi, so the double integral is dash 2 backslash pi. Both methods should yield the same result, illustrating Green's theorem in action. Conclusion: the geometric interpretation of Green's theorem provides a powerful visual understanding of the relationship between the circulation of a vector field around a boundary and the sum of local rotations within the enclosed region. This interpretation helps bridge the gap between abstract mathematical concepts and intuitive physical understanding. That was all. Goodbye.